Hello, welcome to today's session using MATLAB and Simulink to accelerate development for Qualcomm NPUs and DSPs. My name is Adam Cook. I'm an application engineering manager at MathWorks. I've been at MathWorks for about 10 years, and I focus on signal processing, AI, and embedded code generation deployment to embedded DSPs.
Hi everyone, I am Talha Gorsi, AI product manager at Qualcomm, leading software strategy for Hexagon DSP.
So today we're here to introduce you to the Hexagon Hardware Support Package. This is a new downloadable package that connects the MATLAB and Simulink ecosystem with Qualcomm's Hexagon processor, which is part of the Qualcomm Snapdragon SoC. The support package enables algorithms, models, and systems, including those that contain AI, to be deployed to the Hexagon processor. The generated code is going to be well optimized because it's taking advantage of scalar and vector code optimizations, as well as the AI inference engine APIs that access the embedded neural processing unit, or eNPU, that runs on the Hexagon processor. The tool fully integrates Qualcomm's tools into MATLAB and Simulink, which means that an existing MATLAB or Simulink user doesn't have to be familiar with the Qualcomm tools in order to deploy their algorithms. You're going to be able to get production quality code, and you're going to be able to run that code directly on the Hexagon simulator or a Hexagon hardware target. So the key concepts that we're going to cover today is what value the support package is providing, as well as how to get started with using the support package. We're going to use an example of an audio smart speaker model, and we'll show you how you can take models like this that integrate complex systems and algorithms, including signal processing, controls, AI, and you can automatically deploy them to the Hexagon simulator or Hexagon hardware target. We'll cover a concept called processor in loop, or PIL for short, that allows Simulink to communicate with the Hexagon hardware target while it's running. And after the code is generated, we can inspect this C code. We can see that it's integrating Hexagon-specific optimizations. These maximize the performance on the simulator. And we can also utilize performance analysis tools to look at metrics such as CPU utilization and see how well we're performing. Now, a key feature of this tool that we want to emphasize is the ability to integrate AI and machine learning or deep learning with the surrounding pre- and post-processing of a complex system. Note that the AI portion is going to be deployed specifically to the embedded neural processing unit, or the eNPU, on the Hexagon device. The rest of the model runs on the Hexagon DSP, and it's well optimized. In the case of the smart speaker model, the AI portion is the voice command recognition engine, which is a trained convolutional neural network. The automated integration of AI into a complete system, this is really a significant value add because it provides significant time savings versus trying to do this sort of software integration manually outside of MATLAB and Simulink. Now let's take a look at the general workflow for using this tool to develop and deploy an AI system of your own. In some cases, you might already have a trained neural network in existing frameworks such as TensorFlow or PyTorch or ONNX. In other cases, you might want to train in MATLAB a new model from scratch. In either case, these models are incorporated into a new custom block that's part of this package called the eNPU block. And this is how you get your AI model into the Simulink environment. And then once it's in there, you can build up your application design around it. If you've never used Simulink before, it's a really great system for testing and designing complete system simulations. So this allows you to test your AI in the context of the complete system. And you can do full design and verification all in one platform. You can also integrate MATLAB if you already have that code existing somewhere else. After your design is complete, then you can use the Hexagon Hardware Support Package to deploy it using our automatic C code generation capabilities. So now I'm going to hand it over to Talha, and he's going to discuss how Qualcomm processors are enabling AI on the edge across many applications and industries. And I'll be back later to do a detailed demonstration of the support package.
Adam introduced Hexagon Support Package and showed how it creates seamless experience for developers working on Qualcomm's Hexagon DSP, right from within familiar environment of MATLAB and Simulink. Before going into the details of Hexagon Support Package, it is important to understand Qualcomm's AI engine and how it offers flexible architecture that allows AI workloads to be offloaded across multiple compute blocks, including CPU, GPU, Hexagon NPU, and the sensing hub. Each block serves a different purpose. CPU is general purpose and is often used for latency-sensitive applications and for running lighter ML workloads. GPU is suitable for graphics-heavy applications. Hexagon NPU is specially designed for AI acceleration. delivering high performance with optimized power. That's why we offload majority of heavy AI workloads here, particularly for real-time use cases like computer vision and for running generative AI models. Sensing Hub is ideal for always-on, ultra-low power applications. It includes a micro NPU to handle small models like keyword detection or basic sensor fusion, running 24/7 without waking up the main system. With Hexagon Support Package, developers can target both NPU and Sensing Hub seamlessly using model-based workflow. Let's look into the compute subsystems within both Hexagon NPU and the Sensing Hub. On the NPU side, we have three specialized engines. Scalar processor, ideal for control logic. Vector unit, optimized for data parallel operations. Matrix unit, designed for high-performance matrix computations, especially in deep learning models. On the Sensing Hub side, we see a scalar core for lightweight processing, a micro NPU built for ultra-low power inference tasks like keyword detection or simple sensor fusion. What's important is that Hexagon's support package enables code generation for all these compute sub-blocks within Hexagon NPU and the Sensing Hub. We looked at the compute blocks Hexagon support package targets within Qualcomm SoC. Before we explore how Hexagon support package accelerates development, let's first look at Qualcomm's AI stack. We created a unified AI software offering that combines our software capabilities and tools into an integrated solution. Qualcomm AI Stack is a full software development stack from top to bottom, supporting popular frameworks, developer libraries, system software, and it supports multiple OSs. Our develop once, deploy anywhere approach ensures our users can develop a feature or application, then move the same model across different products and tiers. At Qualcomm, we care for our developers. Goal of AI Stack is shortening the design to deployment time so developers can focus on core algorithm development and innovation rather than low-level implementation details. Code generation via Hexagon Support Package is one such effort designed to reduce deployment time. Developers start with either a MATLAB function or a Simulink model to design and simulate their algorithm. With Hexagon Support Package, that high-level design is translated into optimized code using embedded code generation workflow. Under the hood, we use replacement libraries and code generation backends that are aware of Hexagon DSP architecture. So the output is not just portable code, but it is also optimized for execution on Hexagon. This reduces development time, eliminates manual porting, and helps ensure consistency from simulation to deployment. It brings the power of model-based design to Qualcomm's AI-capable DSPs. In this section, we'll look at how Qualcomm's AI engine is enabling real-time applications across key verticals. With arrival of 5G and rapid advancements of AI, we are seeing a new paradigm. The transformation of connected edge has begun at scale, and data processing is happening closer and closer to the edge devices. In the past, AI was completely associated with the cloud. Now we move from this cloud-centric AI of the past to the world where we have partially distributed AI with inference happening on both device and cloud edge and training happening in the cloud. In the future, we expect that not only inferencing, but training will also happen on device. We call this fully distributed AI environment, where devices will see continuous enhancements from on-device learning. Processing data closest to source provides the benefits I mentioned and also helps AI to scale. On-device AI is high performance, low power, low latency, and ultra secure. and we are in a unique position to deliver that future of AI to you today. We take that AI technology we develop in our flagship mobile products and leverage across other solutions like automotive, smart PCs, wearable devices, and others. We call it Connected Intelligent Edge, where all the devices are connected and run on-device AI. Qualcomm AI is enabling intelligent experiences across multiple verticals. From on-device LLMs to AI-powered service assistant in automotive, smart PCs, immersive XR spaces, industrial automation, and optimized edge networks, our AI solutions are enabling real-time, efficient, and scalable deployment across industries.
Okay, thank you, Talha. So now that we know more about Qualcomm's chips are enabling AI on the edge, let's take a deeper dive into what's underneath the hood of the hardware support package. This package is integrating a lot of tooling that Qualcomm offers to support development on the Hexagon. There's two different types of Hexagon simulators that are built in, so you can use this tool even if you don't have access to Qualcomm hardware. In addition, the code generation is taking advantage of existing Qualcomm code libraries to offer optimized performance for math and DSP operations for HVX and QHL. And of course, like all of our MathWorks products, you're going to find detailed examples and documentation to help you get started very easily. As a result of all this integration work we've done, that makes the end user workflow very straightforward. You can build your model in Simulink or write your code in MATLAB, select the Hexagon target platform you want to use, and then with a single button click or line of code, execute a processor in the loop simulation directly on that simulator or hardware. By executing a pill simulation, you're going to be able to gather valuable metrics about your application, such as the CPU utilization and numerical verification of the key signals in your algorithm. Now let's finally switch over to MATLAB and Simulink and do a more detailed demo. Okay, so now we're over here in MATLAB, release R2025A, and we're ready to install the hardware support package. So we're going to go up to add-ons and get hardware support packages. This will open up the Add-on Explorer browser. And then once we're in here, we can just search for Qualcomm. We see the first hit that comes up is our embedded coder support package for Hexagon processors. Let's go ahead and install it. Okay, we'll confirm our selections, accept the license agreement, and it's going to go ahead and download behind the scenes all the necessary files and do the installation. Once the download's complete, we have to go through a setup process, which is what we're going to use to enable the MATLAB tools to talk to the Qualcomm tools. So we just have to tell it locations of our SDK and things like that. Okay, so now we have our hardware setup screen. This is asking us if we've already installed the Qualcomm Hexagon SDK. If we haven't, it'll give us a download link. In my case, I already have it installed, so I can just click validate, and then it's going and looking in that directory and verifying that the installation that I did is valid. Once that's complete, I can go ahead and hit next. There'll be another validation specifically for the LPAI add-on. This is what I need if I want to use the eNPU block, which I do in my case, so I'm going to validate that as well. And finally, if I want to use hardware, there's this thing called the Android debug bridge, which is how I communicate with the physical hardware board. In my case, I'm not going to use that for today's demo, but of course, if I were using it, I would just validate it and I'd be good. For now, we'll just skip it, and that's it. The installation is complete. We can go ahead and hit finish. Now, as a starting resource, I recommend just going directly to the examples in the documentation. That's going to open up this browser window. And you'll find a number of different examples for both MATLAB and Simulink. I'd recommend starting off with, of course, the Getting Started With example as a starting point. This will help you get up and running quickly with a simple example that takes you through the complete workflow. All right, so that's everything you need to know to get installed and up and running. Let's now take a deeper dive specifically into the smart speaker example model. All right, so here is our audio smart speaker example, open up in Simulink. Let's start off by taking a quick tour through the different sections of the model, and then we'll go through the workflow for deploying this onto the Hexagon simulator. All right, so to start off, we have an audio input path up here. Then we have an audio output path down here. And this third section over here on the right is for our visualization and scopes. Let's start off by looking at the audio input path. We've got a signal that comes in from our MATLAB workspace. This is going to be our speech command word. And it's going into the speech command recognizer subsystem. Inside of this, we have three different components. There's feature extraction happening first. That goes into our deep learning classification. This is basically our speech command recognition inference engine. And then finally, there's a bit of decision smoothing, which is taking the output of this deep learning classification and then producing a speech command word. Those are going to be different commands that you give the smart speaker, like start and stop playback or volume up, volume down, those sorts of things. Now, of course, the key here is that we're integrating all of this signal processing and post-processing along with the deep learning all in one subsystem. The deep learning classifier is a special block that we're calling the eNPU block. If we double click on this, we see that the block parameters for this block include an EAI model specification. Now this is a file that's created by the LPAI SDK add-on for Qualcomm Hexagon. And inside this example, you're going to find detailed Python instructions for how to create this file. The input is going to be an Onyx model. So again, if you have a model in another framework like PyTorch, it can be converted to Onyx, or you can train a model in MATLAB and convert that to Onyx. And the instructions that we provide in the workflow example will show you how to create this EAI file. Once the model is running inside of Simulink with this EAI format, all of the connectivity between the signal processing and the deep learning is handled for you automatically. So we take care of all that integration for you. All right, down here on the audio output path, this is our playback engine. So this is the music that's playing out of this speaker. And here you're going to find common audio processing like EQs and limiters and things like that. And when we generate code for these things, we're going to integrate all of our DSP optimizations into the generated code for filters and math and things like that. And then these components over here on the right are things like scopes for spectrum analysis. That way we can visualize and debug our system before we're ready to deploy it. So the common workflow here would be to develop the system in simulation on my host computer first. So if I run it like this, it's going to run a simulation on my desktop PC. And this simulation will run very quickly. It'll run, at real time or above real time. And I can kind of see what's happening with my signals as the simulation is actually running. All right, so it's just a 6-second simulation, so this completes pretty quickly. But for today's purposes, we can assume this model is tuned, debugged, ready to go for deployment onto the Hexagon eNPU. All right, so what's the next step when I'm ready to deploy it? Well, first, I want to configure my hardware target for the Qualcomm Hexagon simulator or hardware if I happen to have that available. For today's purposes, we're going to use the simulator. So there's a hardware tab up here. If it's not showing up, you can always go into apps and just search for hardware, and you'll be able to find that tab. From there, I can select hardware board, and then I could also select specific hardware settings for that board. So this is where we're going to find all the behind-the-scenes connectivity to the Qualcomm tools that we built into this support package. So if the simulator is selected, we're going to get a number of different target hardware resource settings down here, like processor version, which simulator platform we want to use. We can usually use the Hexagon simulator or the QEMU simulator. What is the version of our eNPU? If we want to add a special profiler, so these are the profilers that are built into the Hexagon tools. We also have our own MathWorks-based profiling, which we're going to use today. So we're going to just leave this as none. And then there's a number of other different options that you can use, as you're running your simulation. Now, if I wanted to run hardware, I would select instead the Qualcomm Hexagon Android board, and I'd get a similar set of different hardware board settings for that hardware implementation setting. Now, there's one other thing worth mentioning here under code generation interface. By selecting our hardware implementation target up here, we've automatically enabled the appropriate code replacement libraries. So for the particular simulation that I'm going to run right now, we're going to use the Qualcomm QHL library, which is going to pull in those optimizations for DSP blocks, math operators, math functions for the Hexagon DSP. Notice there's also a Qualcomm Hexagon HVX library. This can be used on select Hexagon targets that have this HVX support. They can even be used together. Okay, in this case, I'm just going to leave it on Hexagon QHL, and we're ready to go. So that's it. Now the system is completely set up, ready for simulation on the hardware, or the Qualcomm Hexagon simulator in this case. To actually run a processor in the loop simulation, you heard me use that phrase earlier, there's a special tab called the SIL-PIL tab. Again, if that's not showing up for you there automatically, just come in, search for PIL, and you'll be able to open up that tab. And then this is where I would set up my processor in the loop simulation, and I could decide, do I want to log signals that I can verify new metrics? Do I want to do task profiling? And I have different options here as well. I could either profile at the top level of my system, or I could go into detailed function level profiling and save all those details as well. For today's purpose, we're just going to do task level profiling and start with that. So I'm going to go ahead and kick off the SIL-PIL button right here, which is in this case, it's going to run PIL, processor in the loop. And we'll start this process. And this is not going to be a real-time process because unlike the host simulation that we saw earlier, now we're not running on the host anymore. We're actually running directly on that Qualcomm Hexagon simulator. So it's a simulated implementation of the Hexagon chip. So naturally, that's going to run a little bit slower than a real-time system. So what we'll do here is we'll kick off the simulation, we'll let it compile and run behind the scenes, and then we'll come back and look at the results that we get once it's finished. All right, so while that PIL simulation is running, I thought I'd give you a little bit more detail on what goes into creating the EAI file that we saw earlier that goes inside of our eNPU block. So the EAI builder is a Qualcomm tool that produces this EAI file. And the input to that is going to be a quantized neural network in ONNX format. There's some helpful tools in MATLAB that can help you create this ONNX format if you don't already have it. So for example, we have a deep network designer that you can use to either design or import existing models into, and it can be used in conjunction with the deep network quantizer. The deep network quantizer can be set up to spit up a JSON file that contains all the quantization information for your network. And then the quantization information can be combined with the exported ONNX from the deep network designer to create one of these EAI files. And this is what we did to create the speech command recognition engine that's running in the smart speaker model that we're looking at. All right, so let's go back over to Simulink now, and we'll look at the completion of our PIL results. So now we're back over here in Simulink, and our simulation for processor in the loop has just completed. Let's start off by looking in the diagnostic viewer and kind of take a look at what just happened. We can see that we generated a whole bunch of code, and then we communicated with the Hexagon SDK tools to compile that code and run it on the Hexagon profiler target. And we can see that right here. Over in this code viewer area, we can look at all the generated code that we produced. There's a whole lot of it for this system. An easier way to navigate might be to actually use the bidirectional traceability, where we can click on different blocks and it'll actually allow us to navigate directly to that section of code. We can look at that code and we can see specific references to QHmath, which are the code replacement libraries that were put in specifically to optimize the code for Hexagon. All right, now because we ran processor in the loop, we gathered valuable information while we were running. There's a couple different things that we can look at. Let's start off by looking at the profiling details. We're going to open up this code profile analyzer. It's going to load up the code profile results. And here we get valuable information such as task execution times and CPU utilization. So what the CPU utilization is telling us is for a given amount of time per step forward in the model, and this is determined by the sampling rate of our audio system and the number of samples per frame that we're processing. How much time are we spending processing those samples? This gives us a metric that allows us to know how much overhead we have available in our system. So we can see here that our CPU utilization was about 17%. This means we have quite a bit of overhead available. We'll look a little bit later on what this number would look like without all the optimizations enabled. In addition, there's raw execution timing information measured in nanoseconds or ticks that we can look at as well. And as I mentioned earlier, if we wanted to turn on function level profiling, we could do that as well. However, it does slow down the amount of time that we spend in the pill simulation, so I didn't do it this time. All right, another useful feature is data verification, and we can use the data inspector tool to do that. So what we want to do in this scenario is we want to compare the outputs from the original simulation to the outputs from the simulation that runs specifically on the Hexagon simulator. So that's what we have here. We have two different runs. One of the runs, run 4, was the data as it was run on the host computer in Simulink. And the other one is the data as it came out of the Hexagon simulator. In this case, the data that we're logging is the output port of the smart speaker right here. So we see this signal over here, and the reason it has this shape is because we start playback of the audio and it slowly ramps up. And then after a certain amount of time, we stop playback of the audio and it slowly ramps down. But what we really care about in this case is, are these outputs matching? So if I just look at it at this view, we can see that the signals more or less look the same. They're right on top of each other. But what's really useful is the comparison tool, where we can get into the details. So if I right-click on both of these guys and I go to compare signals, then I can see the low-level details. And here's where I can verify that I do indeed have a match. There's subtle differences. If we look at the y-axis here, we see that we're pretty much down in the noise region of a single precision floating point data. So in most situations, this is going to be good enough for production deployment. We verify that we're getting the same signal output accuracy within the level of tolerance for the particular data type that we're using, which is single precision in this case. All right, so now we've seen all the different outputs that we can get from doing a processor in loop simulation. And what's great about this process is it's iterative, right? So if I found that I have CPU utilization available, then I can go back and potentially tweak my algorithm to add more capabilities. You know, I could make my deep learning network more sophisticated, or I could make my output processing more capable. Or conversely, if I found that my CPU overhead was too low, I could simplify my system until I get it to the right where it's just the right match for my hardware. Okay, so to wrap things up, we want to emphasize that we're generating production quality code that leverages all the hardware acceleration and DSP libraries that Hexagon has to offer. So as a point of comparison, the red bar on the left here shows what the performance would look like if we're comparing to code that was either generated or handwritten with no optimizations for Hexagon specifically. It's going to use about 250% of available processing time, which is obviously too slow to run as a real-time system. The middle bar here is showing how much improvement we get just by moving the AI portion of the model to the eNPU accelerator. So this is a significant boost. But finally, the last bar is what happens when we turn on all the performance optimizations, including the DSP optimizations for the QHL library. It uses only about 17% of the available processing time. So we have bandwidth available to add even more capabilities to our algorithm if we wanted to. And this represents about a 15x improvement from where we started.
To wrap up, I would like to share how developers can get started with deploying their algorithm on Qualcomm's AI hardware using Hexagon Support Package. For those interested in hands-on deployment, Qualcomm collaborates with Lantronix to provide development boards. These boards allow you to test your AI models directly on Hexagon NPU and the Sensing Hub, the same blocks used in commercial Qualcomm SoC. This opportunity is not only valuable for industry developers, but also for university researchers and students looking to explore edge AI. It's a great way to go from simulation to deployment and experience Qualcomm's AI hardware in action. We look forward to seeing what you build.
Okay, so that brings us to the conclusion of today's session. We'd like to leave you with a few useful resources for next steps in these areas. This link over here will bring you to a page where you can learn more about AI and model-based design with MathWorks tools. And this link over here will bring you to a page where you can learn more about the Qualcomm Hexagon NPU. And then finally, this link here, of course, will bring you to the download page for the Hexagon Hardware Support Package. We hope you found this session today informative, and you have a good understanding now of how you can take your embedded AI application to production with tools from MathWorks and Qualcomm. Thank you.